So today we'll have a lecture and we will cover the final topic. We will cover dynamics. Dynamics of rigid body, just a single rigid body, and then we'll proceed to dynamics of a serious chain of links. And you will be able to model dynamics of any robotic system that composed of rigid body links. The same theory can be applied also for the elastic bodies, but it's a little bit more complex theory, more complex example. And if you're interested in it, you will be able to cover this material by your own. So the goal for today's lesson, the first lesson, is to cover the essential stuff about dynamics. We already covered it a little bit, but we only covered one deep problem and also a planar robotic system. So right now we will consider a motion in 3D Euclidean space. So we will going to elaborate something that we already know. Let me share my screen. Can you see it now?
Yep, it's fine.
Great. So agenda for the day. Agenda. So the first lesson will be focused on dynamics. So spatial dynamics. And the second lesson will be about Mujoko. So I asked Valeria to give you a workshop on Mujoko. She is very experienced in this kind of material, and he will give you the foundation of your future knowledge. If you already know the basics, I believe it still will be beneficial for you to consider this once again. So also you can ask her questions. She uses Mujoko simulation on a daily basis. So this is something that she got used to do. And you can ask any questions as for a practitioner, right? So the next lecture lessons, practice lessons, will be with Igor, and you will be focused mainly on projects. Consider, yes, here you can see Igor. He's an official instructor for this subject, and you will be working with him on projects. So right now, our goal is to cover the rest of the theory material, and Valeria give you the first steps for Mujoko, such that after that, you'll be able to cover the rest of the material by your own, using the official documentations, tutorials, etc., etc. Is it clear? Any questions?
It's clear.
Nice. Okay, so before we proceed, so let us start the lecture. And this material, the spatial dynamics stuff, spatial dynamics, will be focused on something that we already know. Will be focused on Lie groups and screw theory. Since it's been already 2 weeks since our last lecture, let me cover a little bit something that we already know. So we covered something which is called R, rotation matrix, that belongs to something which is called SO3, like a special orthogonal group, or orthogonal group, and we use R to describe orientation of a rigid body in 3D space. In order to describe the general motion, we using something which is called homogeneous transformation matrix. It is denoted as a H, and it belongs to the SE3. It means special Euclidean group. All right, and H can be used to describe the general motion, and the basic way how to describe orientation can be considered as sorry. So let me write it explicitly. For example, we have a position vector P of a physical point P, and described in some frame I, for example. And we would like to know position of the same physical point P, but not in frame I, but in frame J. If we just consider rotation, we need to multiply on the rotation matrix. But if you would want consider the general motion, in this case, you need to use H. And here you can see that this P is small, and on the bottom, here P is a capital. All right. And as you probably remember, H for the one that we already mentioned will be R J I P J I 0, 1. So it's 4x4 matrix, which is needed to describe general motion. And this P, and this capital P is this thing. So capital P equal to the small p with a 1. So it's a column with 4 entities. So then we consider something which is called angular velocity, and we found that we can use skew symmetric representation of angular velocity. For example, if we would like to consider a motion of body I in respect of frame J, and the motion considered in frame J, in this case, we need to, there's a mnemonic rule, we need to use this symbol right here, opposite symbol here, and we need to take a look at the same configuration of scripts, and thus means that we need to put a dot on the left side. And we can describe the same motion I around J, but we can express it not in frame J, but in frame I. And in this configuration, I, we need to put here, J here, and the dot will be not on the left, but on the right. So you can see that if you swap position, the R is a group, a special orthogonal group. It has properties of associativity, neutral element, inverse element, closure, but it does not commute, and this means that if you swap position of these matrices, the result will be different. And basically, in this case, you will have the same motion, but expressed in a different coordinate frame. So it's something which is called angular velocity. Then we know that we also can describe linear velocity. And in order to do this, so we can do the following: I, J, for example, I, and we need to use a rotation matrix, J, I, and a P dot, time derivative of a position vector. So it will be linear velocity. And then we also covered something which is called twist. So twist is basically the same stuff, but for homogeneous transformation matrix. And we need to put a dot where? On the left or on the right? Where should I put derivative sign?
Left. On the left.
On the left. Great. So it is twist. And twist something else that can be used to describe velocity in terms of a position of a screw, and the screw is an axis of rotation. I hope that you remember this stuff. And also, finally, what we covered that both of these equations, not this equation and this equation can be treated as a differential equation, and in order to solve it, you need to use exponential coordinate representation. And in this case, R will be equal to exponent to the power of twist, Q, like this, times the initial R, it's like initial state. And the same for the H. It's a bit more precise, I believe. H0. All right. So there were also something which is called Rodriguez formula that we can use. Let me write it here. So it is something like sinus theta plus omega squared by 1 cosinus theta. And it is called Rodriguez formula that can be used to calculate R. So if you know your angular velocity direction, if you know the offset position change, if you know this stuff, you can compute rotation matrix out of this formula. Similar stuff can be written for the H. It's just a little bit bigger. You have it in slides and you have it in your lecture notes. So I'm not going to write it down here. And finally, then we cover Jacobian. It's not related for the dynamics of rigid body, so I'm not going to repeat it once again. You can find it in the textbook. All right. So now we have covered the important stuff that we're gonna use it today. So far, do you have any questions? Okay, good. So let us proceed to the rigid bodies dynamics. To the main topic of today's lesson. So, can you tell me the equation for a point mass for kinetic energy? So kinetic energy here, let me write it implicitly, explicitly, kinetic energy of a point mass. What it will be?
Half MB square.
Yes, it's something that we got used to, right? It's true if V is a scalar. So if your V is not a scalar, if it's a vector, in this case, it will be different. So you need to take a transpose of your vector and multiply it on the vector. So this will be kinetic energy if V is a column. So basically, if it's a vector, not a scalar, right? And if you have several bodies connected in a series, what will be a total kinetic energy of this series? So could you tell me? For example,
A vector sum of all the velocities.
Right. So if your robot consists of I elements, so let us consider that robot consists of I elements. In this case, the total kinetic energy will be kinetic energy of the first body, of the second body, plus plus Ti. So you need just to sum it, right? And the same is true for rigid body. So let's assume that this is a rigid body with a random shape, with a random velocity. So we're trying to be general, right? Since when we talk about robotics, when we consider robots, we do not operate with a point mass. We operate with the rigid bodies, with the different densities, with different shapes and so on. So here we need to be general. So this will be our body. Okay. And let us consider a very tiny piece of this body. So this is a very tiny piece is called infinitesimal piece. So it's the tiniest piece that you can consider. And we can say that the mass of this body is delta m, dm. So the dm is the mass of the smallest possible piece of this rigid body, all right? And in this case, dm equal to the density rho times its volume. And the volume is still very small, so it's infinitesimal volume of this tiny piece. And we can say that there is some frame C0, and we can describe the position of this infinitesimal piece as a P0. And then let's assume that the body itself has also a frame. Let me use a different color. So let's assume that it also has a frame, Psi. And in order to describe position of this infinitesimal small piece of a body, we can use another vector position, P. And what kind of superscript should I use here? So here it was 0, since we described position of physical point P in frame 0. Here, what do we want? We want to describe the position of the same physical point P, but describe in a frame I. What kind of superscript should I use?
I guess.
Sure. So this P and this P, they show position of the same physical point, but represented in different frames. In a frame Psi that belongs to a body, which is physically rigidly connected to a body, and a Psi0, which is something else that is not connected to a body. It can be another fixed rigid frame. You can consider it a world frame or a space frame, or it can belong to another body that also moves. Here we trying to be general. All right. And we can write kinetic energy of this infinitesimal small volume dm. So kinetic energy of this tiny piece will be 1/2 dm times velocity, and velocity here will be p dot. Here we do not need twist, we need, wait, was this stuff. So p dot in frame 0 transpose. Let me here. It will be, the result will be the same mathematically speaking, but it's just the way how they write it down. So basically this is V transpose, this V times V transpose, it will be the same result as a V squared if you consider scalars. So basically it's the same equation that 1/2 times mass times velocity squared. Do you agree?
Yes.
Yeah,
Great.
But I have a question.
Sure.
Here, this equation suggests that dm is also a vector, right?
dm here is a scalar.
How can we? It's a scalar.
It's scalar, yes.
So b is written like r b to the transport. It's a column.
So this is the column. This is the row, and this is the scalar.
So if b transpose is a row, it need to be multiplied with a column. It can't work, right?
So this is yeah, you can multi. So look, vector space. What kind of properties it has by default? You can sum vectors, and you can multiply a vector on a scalar in order to scale it, to shrink it,
Okay.
to increase it. So dm is a scalar on a vector.
Yeah. It's a dot product. Sorry. Yeah, I thought it's a vector product. Okay.
It's not vector product.
Oh.
It's product with a scalar. So dm
Yeah.
is something that scales velocity.
Understood. Thank you.
Thank you. All right. So what should we do here? We need to proceed from this tiny piece to the whole rigid body. And because of that, we're gonna write it a little bit in a different manner, since we know that dm is rho times dv. We can put it right here. Rho dv p dot 0. And since it's just multiplication, we can switch it a little bit, I mean, position. We can put dv right here. And what we'll get, let me change. And since p is just a scalar, we can also swap position, and we can do this stuff. So basically, this is v squared. This is the rho, and this is the volume of the infinitesimal small piece of volume of the rigid body that we consider. So p dot 0 is a velocity of a body expressed in frame psi0. And also I need to change a little bit p rho, that actually rho is not a constant, it's a function, and rho depends on p, not dot, pi. So here you need to be cautious. So it's not p times, it's not rho times p. It rho that depends on p. So density is not a scalar. I mean, it's not constant. It's not constant. Density rho is a function of move it. Of pi. Look, pi is a position where the piece of rigid body that we consider is located. And you can think of a link of a robot, like, right? So it's not a homogeneous piece of material. It's a artificial link that consists of a range of different objects. So there's the body of a there's a metal part, right? There's a motor there, there's sensors, etc., etc. There's volume, space with the air, right? So robot link is not a homogeneous structure, and the density of each tiny piece is different. So for the homogeneous brick, for example, steel brick, the density will be relatively constant. It's still not constant, but still we can consider if we have aluminum brick, if it's plastic brick, the density is constant. But for a robot, it's not the case. Is it clear? That the density is not constant.
Yes.
Great. So what do we have here? 1/2 function that depends on the position, and it equal to the density of this piece, and then P dot transpose times P dot dV. And this is kinetic energy of a tiny piece. And if we want to get a total energy of a solid, it will be the following: total energy of the whole body. So pretty much the same idea that for a robot that consists of I elements, we need to take a sum. And what should we do in order to take a sum of these infinitesimal pieces?
Integrate.
Right.
Integral.
So we need to take an integral of it. So kinetic energy will be the integral on volume. It will be 1/2 rho, that depends on pi, p dot transpose 0, p dot 0 dv. This will be kinetic energy of rigid body. But since it's kind of messy, we would like to rewrite it. And in order to make it simpler to understand, we need to get rid of all constant out of the integral, right? So if you have something constant in the integral, you can take it from integral, right? Is it clear? For example, the integral of something like 2x dx, you can take this 2 out of the integral. Do you agree?
Yes.
Yes. What will be constant for a rigid body?
Distance between 2 points.
I'm sorry?
A distance between 2 points.
Distance, okay, distance. Is it helpful for us? Because look, kinetic energy is a function of velocity, right? So I can write here that t is a function of velocity. So the kinetic energy is a function of velocity. So we need something that can be treated as a velocity, and it's constant for each piece that belongs to a rigid body. What kind of velocity is constant? I mean, not constant, but the same for each point within this volume.
Center of mass. Velocity of center of mass.
It's true if you do translation motion. For
Okay.
general case, you also have angle velocity.
Okay.
What can you do with that? Because here we need to be general. We need to describe spatial motion.
We can transform the frame of reference. We can write the equation in different frames of reference of frame.
Okay. What if we would like to make our lives easier? We spent several lectures on kinetic.
Moment of inertia. I omega.
I'm sorry?
Moment of inertia, I guess. Sorry.
Look, we were considering spatial motion, right? Where it was. So the spatial motion of a body. And we found that there is something which is called twist, right? And twist doesn't the twist does not depend on your coordinate transformation, and it will be the same for each point on the body. Do you remember that? The twist in the particular moment, it will be the same. So if you freeze time, for example, for the you do simulation, you have steps, integration steps, and if you freeze it for the integration step number n, the twist of each point that is connected to a rigid body will be the same. And this constant stuff, it's constant for this particular moment of time. For the rigid body motion, actually, when the body moves, we consider that the frame that is connected to a body does not move. It's stationary. But for each moment of time, it's just another new frame that relates to the particular moment of time. And if we freeze the time for this particular moment, the twist will be the same, will be constant for this particular moment. So if we represent kinetic energy in terms of twist, we can get rid twist out of the integral such that the equation will be much simpler. Do you see the idea?
Yes.
All right, let us proceed then. So our task here is to make this equation, to make it simpler. Let's try to do this. So we know that P0 will be equal, let me change it a little bit. So if we have Pi, position of this infinitesimal small piece in frame I, if we want to go from the local frame representation to the zero frame representation, when the zero is considered as a space frame, this will be like this. You can take a time derivative. You can easily prove that the velocity will look like this, since p dot I will be constant. And we can rewrite this h dot in terms of twist. So let me do this everything explicitly, such that you can believe me. So h01 pi plus 0 I p dot I, it will be 0, since this stuff is constant, pi, this stuff, since frame is rigidly connected to a body, and the position between some point on the body and its frame will be constant, the derivative constant is equal to 0. And then we know mnemonic rule for the twist. So we have a body I that moves in respect to 0, and we want motion in expressed in the body frame. In this case, I goes here, 0, 0, and that must be not here, here. And we can write that h dot 0, 1 equal to this h inverse, h I0 inverse twist ti0 I. And if it's inverse, we can just swap the superscripts. So this step. P dot 0 equal to h0 I twist I0 I pi. And then we can we can take this P and we can put it inside the equation that we just derived. So it has P dot, and we just derived P dot. And we know that the twist is the same for each point of a body that moves in this space. It's something that we would like to do. We would like to see twist inside integral sign, such that we can go it from the integral side. And the rest, the rest of the stuff, like that one, will be in the integral. And it will be easier for us to take this integral. This is the motivation. So let us proceed with this equation such that we can make it even simpler. So Actually, we cannot just take this stuff and put it there, since this is not actually it's not that P, it's a capital P, not a small p. And we need a small p to put it there in the previous one. So P capital equal to small p with a 1. And so P is a column that has 3 entities, 3 entities, and P has 4 entities. We need it just to make our matrix represent multiplication. You need the same dimension to do the multiplication. So P dot will be, the capital P dot will be equal to the P dot 0. So now let us rewrite this stuff, and we will get small p dot 0, 0 equal to, here we have h, and we know that for the h it will be a 4 by 4 matrix, and we have rotation matrix inside 0, 1. Then the twist. We know that twist is a matrix that has angular velocity in screw-symmetric matrix and the velocity linear. So angular velocity I dot 0 I v I comma 0 0 0, and just p, the same stuff. So capital P equal to the small p I with an I. And what we need to do is to do just a lot of matrix multiplication. We're gonna skip that. I'll just show you here the result. So this is the stuff that I just have written. By the way, all these slides already available to you at the Yandex Disk. So let me just remind you if you do not know how to, you can do with that. So this is our Telegram channel. Here you can see the pinned messages. Here you can find the link for the previous material. So you can see that it's 21, and you can find all these materials. So this is slides for the dynamics. You can find all material here. Okay. Just a reminder. So we have written this formula, and you can do this metric representation, and you will get a lot of mamba jumpa here. We're not going to derive it. It just we're gonna waste a lot of time. But I will write down the final result right now. So the p dot equal to this stuff. Let me rewrite it to you here. So we can find that the p dot 0 equal to matrix R 0 1, then skew symmetric representation of pi R 0 1 times t I 0 1, right? Where t, this twist is twist in the vector form. So this ti0i equal to the angular velocity I0 I v I0 I. It's not matrix form, it's a vector here. That have 6 entities. And that this twist T0 I0 will be the same for all points over the body. So we can take it out from under the integral. And it's something that we wanted to do in first place. So let me rewrite this stuff that we already derived before. And it was like dm. Actually, this stuff. The part under the integral. So dm equal to the 1/2 density that depends on pi. Then we have p 0 transpose p dot 0. So it's the velocities dv. We're gonna work only with the velocities. So we know now that p dot 0 equal to this stuff. Right? And transpose of this stuff, you can easily compute that you need to transpose of this stuff. When you do transpose, you need to swap position. So it will be T I 0 I transpose. Then these brackets transpose, and there's just a lot of multiplication, another multiplication, transformation. I will give you the final result that the velocity will be t. Okay, so let me just write it here. So if you do the transpose, you will get p, p in the skew-symmetric form I transpose R I O R O I. Still, the whole derivation you can find here. So this is the stuff that I just have written for you. So you need to plug into this stuff must be plugged into here. This stuff must be plugged into here. And what we will get? Let me write the whole stuff. So dt equal to 1/2 rho pi, then all this stuff with the transpose p t I o I transpose rho transpose r I o r o I minus r0 I p r o I twist dv. Do you see, I mean, is it clear how we derive this equation? The procedure, the idea, is it clear?
Yeah,
Is it yes? I know.
yeah, almost clear.
Okay. So this is the kinetic energy of infinitesimal small piece of body. And we know that the twist is the same. We can take it out of it, the integral. And the rest of, and 1/2 also constant. So the rest of the stuff, this rho and all this mamba jamba, is something which is called dm. So dm will be p I t rho I minus r transpose. So this stuff. Then density dv, where the dv, once again, it's volume. This is density. This is stuff that changes. So this stuff that is not constant. And dm is nothing else as a mass matrix. It's mass for rigid body. And let me just show you slides. So something that I have just written is a dm. And if you then put this dm right here, you will get that dt, the kinetic energy of infinitesimal small piece of body, equal to 1/2 times twist transpose dm times twist. And the dm is this nasty stuff. And then you can plug everything into the integral, and you finally will get that the kinetic energy of a body equal to 1/2 twist transpose this nasty stuff times twist. And finally, the kinetic energy will look like this. So it's pretty much the same equation. It looks similar to the kinetic energy of a point mass. So the point mass that we started our lesson today from a kinetic energy of a point mass. It was 1/2 m v squared. For the v, if v is a vector, it will be 1/2 v transpose m v, right? So I here is called inertia tensor. So it's a mass of rigid body that moves in a space. And how can we compute it? Basically, this is the formula that we have just derived from scratch. So we have done everything from scratch to derive this equation. So now you can see that we haven't just done it from, not you cannot, you do not need to believe me from blue eye. I don't have any blue eyes, but still, it's not just my imagination. We derive it from scratch, and I try to explain you every detail. Maybe it's still not clear, and this is why you need to do your own research on that. You need to consider lecture notes, you need to consider slides, and the textbooks of Kevin Leach that I already mentioned a lot of times. So if we put this dm to the integral, we can compute the whole energy of a twist. Of a body. So if you consider a body, we'll already know how to compute twist. You can compute it out of homogeneous transformation matrix, for example, or you can use exponential coordinates. You can use screws, screw theory, all these axes and exponential coordinate representation. So there are several ways how can you compute twist. And now we need to compute the inertia tensor. So the inertia tensor, how can you compute it? You still have formula. We know the origin of this formula, and we can compute it. So this will be the result. So it is 6 by 6 matrix, and the left up part of the inertia tensor is related to the angular velocity, and this stuff is related to the translation motion. So this is just matrix, not matrix, it's just mass m times identity 3 by 3 matrix. So it's basically 3 by 3 matrix where you have m's on a diagonal, on the main diagonal. All right. And for the general case, the inertia tensor looks like this. But if you choose a special one, a special frame, a special coordinate frame, you will have just like P, this capital P with a tilde equal to 0. And you will have only elements on diagonal. If you will find such a frame, this frame will be called principal frame. And basically, it is the center of mass of a body. So you can do coordinates change transformation for inertia tensor. So we know that you can change a frame for the twist. So here, look, you have a twist of a body I that moves related to the frame 0 expressed in I. And here we have the same motion in K. So if you have initially motion in so actually here you can see consider changing a frame for a twist Ti. It's actually changing twist for the for this part. So if you have initially motion for K, you can represent it for, you can change the frame such that the same motion will be represented according to the frame I. Look, then we just need a joint matrix multiplication such that the same motion of a body I that moves in respect of body 0, it will be expressed not in K but in I. So you can change the frame of representation, and you can change coordinate representation for the twist such that the motion will be represented in the principal frame. And this is why we need here a joint matrix. So we need a joint matrix such that the motion will be considered not let me change. So such that the motion will be represented not in some random frame I, but in a special one. You need to represent the motion using, you need to use principal inertia frame. So this is the frame such that it coincides with the center of mass of the link. And in this case, you will have only elements on a diagonal. For example, when you do CAD modeling, you can compute this, the CAD software compute this inertia frame for you. When, for example, you have created your robot using CAD software, then you need to represent the robot using universal description format for robots, which is something which is called URDF file. The software does it for you. It finds principal inertia frames such that the elements will be on a diagonal. It can be in vice versa, so you can also find another frame. Generally speaking, you still can do this if you want, for some reason. If it's not possible, if it's not possible to compute where the center of mass is, for some reason, but CAD software can do this for you. So, and the final inertia tensor will look like this. So you need to change your coordinate to the principal frame, and it will be very easy for you to compute principal inertia frame. You don't need it by your hands. You do use software to do this. I'm just explaining you the idea. So, and finally, kinetic energy of a rigid body that moves in this Euclidean space will look like this. So 1/2 twist transpose times inertia frame, inertia tensor times twist. And if you compute it, basically you will get the same result as on the second line. And on the second line, it's something that we're already familiar with. So in the beginning, some of you mentioned that kinetic energy of a point mass, it's 1/2 mv squared, but it's only for point mass. For rigid body, you need also some kinetic energy which is related to the rotation. And you need to consider each angular, each axis, x, y, and z. And this is why you have an extra 3 terms. Is it clear? At least the general idea. Is it clear? Or not? Any questions maybe from your side? Hello? Are you here?
Yeah, I think it's clear.
Are you with me? Great. So every detail, maybe it's not clear. For now, our goal is to get the intuition of this process. How we can go from planar case, from point mass to the spatial one. So the whole idea was that we do derive kinetic energy of a infinitesimal small point, and we treated it as a point mass since it's very small. And then we proceed to the integral, since the kinetic energy of a system is just a sum of kinetic energy of each part. And then we come up with a general equation for a sum of infinitesimal small pieces. And then in order to make the equation simpler, we have rewritten it, rewritten. So we got it in a way such that it depends on twist, and twist is the same for each point, and we can get it from under the integral, and under the integral we will have only components that is not constant, that variable. Also we have density and volume. And the result of this integral is something which is called inertia tensor. An inertial tensor you can calculate by your own, but for the complex shape, it's not possible to do analytically. You need a finite element analysis to do this. So basically, you need CAD software, computer-aided software that will compute it for you. And then, so you do this SolidWorks, NX Fusion, or I don't know, any CAD software can do this. You create a model, then you use it to generate URDF file, and then you can plug this URDF file to any simulation package. You can do this for Mojoko, Gazebo, Bullet, I don't know, anything. So here I have just an extra piece of slides. So momenta for the point mass is just mass times velocity. Pretty much the same for the spatial case. Inertia times twist will be momentum in screw theory. And here is something that you can take a look by your own. So here is just, look, we can write momentum in a body frame or in the inertial frame, basically in the space frame. So for the space frame, inertial frame, it will be like this. But if you would like to derive it in a body frame, you need to do this adjoint matrix multiplication. So here there is a derivation. I do not want to spend time on that. I believe it's another half of an hour. We do not have this. But if you proceed just step by step using the slides, you will get something like this. And if you continue, you will get this equation. This is the momentum for a body expressed in body frame. And you will see that this the range and something else. And if you multiply it with a twist, you will get power formula. So like this. And since you're familiar with this bond graph idea, you will get this bond graph that basically tells that 3 it is power that have been applied to a body. I, this is the power that been stored as a kinetic energy for a body. And this strange piece of symbols is something which is called gyroscopic effect. Look, this handle change its orientation. And it's done only because of gyroscopic effect. Yeah, this is the video that I wanted to show you. And it is done because of this stuff. And you can compute it by your own right now. Okay, so we have like 10 minutes left. Let me proceed to the final step. So we compute the kinetic energy of a rigid body, one single rigid body. And we already know the Lagrangian formulation. We have covered it when we have considered 2R robot. Pretty much the same is true here. So we need to compute the sum of kinetic energy of each body, and we know how to do this right now. We can compute each kinetic energy of each body, and then we need to sum it. So we need to sum it. How can you compute twist? You can use Jacobian. We have covered it on previous lesson. So this will be the kinetic energy and something in the between Q. So Q is the angular velocity of a joint, and this stuff is called mass matrix. So it's mass matrix, and you can derive it for each body. So it will be like mass matrix for body I, for body 1, body 2, body 3, body I. Potential energy is easy. It's basically just the same as it was for the 2R robot, but you can grab this data from homogeneous transformation matrix. You just need to get the proper component of this H. And basically, you need to derive something which is called Robert's motion equation. And it's easy. So Lagrangian equation is just the same as we already know, kinetic energy minus potential energy. Here, something that maybe will be better for you if we'll read in the book, because we don't have any time here to consider this information. But it's very well written in the Kevin Lynch book and in the Murray book. I encourage you to take a look at there. But if you follow all the stuff, you will get this Christoffel symbol, and basically what it tells us that the C matrix, which is related to the centrifugal and Coriolis forces, which is called also dynamic bias, actually is a derivative of mass, not in terms like integral derivative. No, it's something that is it is not independent. It depends on your mass matrix. And if you know your mass matrix, if you know your M, that we just we have spent the whole lecture how to compute M. And if you know M, you can compute C out of it. So look, there is something which is called Christoffel symbol. This is the Greek letter. I do not know how to pronounce it. In Russian, it's look like G. Let's say that it's G, but I'm sure it's not. So if you
It's gamma.
gamma, okay.
Yeah.
Thank you. So this is gamma, and you can compute it if you know your mass matrix. And if you do this gamma times the vector of velocities will equal to the C matrix. So, and basically it's something that any simulator do for you, or if you would like to do this analytically, you can use framework like Pinocchio. It will also derive this component for you. If you would like to consider every detail, you can find practice and practice number 4, and you will be able, yes, it's archive, but if you will open it up, it will be a script for MATLAB. So before we have done this course in MATLAB, and for the MATLAB, there was a script how to do this symbolically. It's a very great script to understand how everything is derived. And there is a small script. How can you derive C matrix if you know M? You can find it there. It's very simple, but still, this script is done not for the it's done only for education purposes. It's not efficient code to do actual simulation, but for the education purposes is great to understand how it works. Also, it's it's great written, very well written in the Murray book that is called like Mathematician Foundation, etc., etc. I do not remember the exact title, but the book is mentioned in the syllabus. Basically, yeah, a final word about J. J is potential forces, and in order to compute them, you need to take a partial derivative to your potential energy in respect of generate coordinates. It is the same as we already done for the 2R robot. So once again, J is the same. C can be computed out of matrix M. How to compute mass M? So we have spent the whole lecture trying to understand how to compute M, the mass matrix. So I believe I gave you the intuition how to do this. Then right now I encourage you to read the corresponding article in Ken Lynch book. It will be very beneficial for you. And the rest of our material and example you can consider it by your own, since we do not have time for that. But I believe that the main stuff that must be given such that to make your life easier, I already gave you. And now you can do by your own. So do you have any questions? Any questions? No question, right?
Seems that way.
Okay, so I believe you need some extra time to consider this material with your own pace. So I'm going to put all the recordings to YouTube and VK. So I came back from the conference, and I believe that I will have time to do this. So I will be placing all the recordings such that you will be able to take a look at once again. And the rest of the classes will be with the Yegor and the guys that I asked to give you like a workshop. So the next lesson that we will have in several minutes, yes, in 20 minutes, so it will be in 20 minutes, will be about Mojoko, and it will be given by Valeria. She is an engineer at the Robotics Center, and what she is doing, basically she is responsible for all our models of the robots that we produce. And she is very experienced in these models, URDF files, Mojoko files, and how can you do these files in order to do the simulation. So you can ask her any question regarding this stuff. So this is like announcement, and I believe that that's it for the first lesson. If you have any questions, you can write me in Telegram. You can write in the chat. You can write in the Telegram chat, and let me know if you have any troubles. So right now we have a break for 20 minutes, and in 20 minutes we'll proceed with the Mojoko. Okay.